Today we will cover OpenMP in depth, mainly because OpenMP is an important model for parallelism. Again, could you please show your hands saying who has used OpenMP before? I know some of you have. Yes. OpenMP, I think you have used OpenMP before. You have used OpenMP? Yes. 2, 3. Okay. So basically, this class has several pockets of expertise. So I will cover all your needs. Today we will go into OpenMP. We will show you what practicals you have. And then later you will have an open coding challenge in OpenMP. We will help you. Okay. I think I can also do it. So I hope to cover some MPI also later today, just because MPI is an important API. And tomorrow and day after, there will be others talking from industry, and I don't want to get delayed introducing basic material. So when that website starts working, you should be able to see a fair amount of material. What you will see, if you are lucky, is this directory listings content. Important programming concepts, etc., but session slides and useful references. And if you go to the session slides folder, you will see session 1 slides, session 2 slides, then session 2 practicals, session 6 practicals, session 7 practicals. These are the practicals that we will be doing today. Let us open some of these. So session 2 practicals is simple material that we covered yesterday, but you can try it out. So one of these sheets will look like this. We can make it available, print, or put it on display. We'll say goal, understanding the basics of floating point. You can ignore this script file. This is for our internal reference in case we get confused. We have a certain file we keep a master copy. But basically, you'll be doing CD, make all these, and then try different numbers, and then tabulate a few results, and compare and write conclusions. This is a little assignment we'll assign you like that. Then we will go to observing the consequences of non-local accesses. Instructions will be, again, make files and all have been pre-programmed to make it very simple for you. So you just say make source equal to that. Sometimes you say make source equal to something, parallel library equal to something, compiler equal to something. So that way it's easy for you. And then you can observe the timing for bad locality, good locality, then read the source code for these sources, write your observations, like that. So fault sharing, there is an exercise providing different numbers as padding. You will get a copy of these. You don't need to, if you want, you can take notes, but you will get a copy in the lab. Similarly, go observe the data races in Java programs. So that's session 2, which is material that we covered yesterday. Session 6 will be today's practice. So that will be covering understand address sanitizer. We will talk a little bit about that. The main idea is that when you program in C, it's extremely easy to omit simple commands. So if you want to have an array of size 8, let us say, then you have to malloc 8 times size of int. But sometimes people just put 8. And what happens is that you're not allocating a large enough array. And these are all bugs that unfortunately one gets to introduce. And so address sanitizer, this is the leak is not that. Leak is forgetting the free command. Often you forget to free malloc data. Often you forget to free allocated MPI types or MPI communicators. A lot of objects are allocated. You forget to free. What happens is memory leak. Memory leak is inaccessible memory. Inaccessible memory causes slow death of the program. So after an hour of simulation, you'll see things crash. So it's good to detect these. And fortunately, these technologies exist in modern GCC, which many people didn't know. Even my postdoc didn't know. It was in Clang, but GCC is important. By just applying some flags to GCC, it'll tell you memory leaks whenever it can detect. These are best effort tools. Similarly, there is a address overlap. So if you didn't allocate enough separation between threads access regions, during runtime it will start detecting whether their memory regions are overlapping. And again, that's a bad thing to have. So this sanitize equal to address will tell you that. It also has data race detection built in directly. So it's just GCC file, thread library, math library, sanitize equal to thread. Just like that, it starts finding data races. So it's a lot of powerful technologies that have been rolled into GCC. It's good to know that and start using it whenever you program. Then, yeah, we will have exercises on handling thread allocation and failure to allocate gracefully, things like that. So I will not show you all the sessions. This is how the sessions look. So today's agenda will be beginning with a recap of yesterday's lecture, and then see how some of the points we introduced yesterday start applying today. So one of the main points that we emphasized yesterday was how Amdahl's law tells us how much parallelism and speed up to expect in a program. If you have a serial region in a program, that essentially dictates how much speed up you can get. Just as a quick calculation, if you have 0.8% of the code serial and 0.2 of the fraction of the code parallel, you get a theoretical maximum parallelism of 1.25. It's basically 1 by, the calculation 0.8, because 0.8 is the serial portion. The parallel portion gets blown away by the number of threads. So that's a good message to keep in mind. And even the work and span idea that we discussed yesterday was saying the same thing. If the span of the program or the depth of the program, these words are used interchangeably, is very long, that means there is a long critical path, which is the serial bottleneck of Amdahl's law. And the theoretical parallelism is T1 by T infinity, where T infinity is the span. So as T infinity goes higher, you get less and less benefit out of parallelism. How it impacts you is whenever you put anything in a serial region, like you use locks too much to protect shared data, that is a serial bottleneck. So instead of locks, you have to look for a better primitive or avoid using the locks, change the algorithm. Needless barriers. It's very easy to write an OpenMP program where you introduce barriers. And in OpenMP, there are implicit barriers at the end of many commands, many sections. And if you know that those barriers exist, you can avoid using those constructs. So anything that is serial is slow down, and it's good to start knowing that. There is no automatic tool for everything that you do in parallel programming. So in many things, it's human responsibility these days. So parallel programming is a lot of concerns, a lot of which are, some of which are supported by tools, the other by humans. You had to really engage and use pre-existing tested code, use good patterns. Okay. So this is all the practicals that we will be looking at, and I already told you what they are. Data races are, again, things that you get rid of. And I'm going to emphasize that a lot because I see, even in my own parallel computing education circuits, whenever I do, data race detection is mentioned, but it's not supported by tools. If you read Dr. Pacheco's book, he says data races are a worry. He points out in 7-8 places data races are a worry, but there's no tool. So it's almost like telling there is some danger, but there is no cure, you know. You have to provide tools. Tools are the ones that help us make way in parallel programming, and tooling is in its primitive stages in many cases. Okay, right. Yeah, so this is the recap I said. Amdahl's law, I already said 0.8 serial means that's the problem, etc. Okay, I have done that. Right, so now we will start the lecture proper and talk about OpenMP-based parallelism. Okay, so basics of OpenMP are, OpenMP is a standard that was created around 1998. It has taken so much time to mature and become useful. Many initial OpenMP's implementations were simply unusable and slow. Even just writing a hello world program in an OpenMP compilation used to slow it down, but those days are gone. OpenMP is the main path that is getting adopted at Lawrence Livermore Lab, all the energy labs. In fact, GPU programming is going to be approached through OpenMP in those labs. The OpenMP 4 has a GPU offload command, which takes an OpenMP annotated region and offloads it into a GPU. So many of the GPU programs will be approached through OpenMP. Yeah. Even debugging GPU programs is going to be approached through OpenMP, meaning once a program doesn't behave well on the GPU, they have a reverse compilation which brings back the code in the GPU as an OpenMP that you can use. Okay. The main person who promulgates OpenMP is Dr. Tim Madsen of Intel. If you really watch his video series on YouTube on OpenMP, you can be an OpenMP expert. He has such good, well-designed videos. He's an animated speaker. So you should really follow all his YouTube videos. And everyone who teaches OpenMP does that. The other resources are, this is an excellent resource on OpenMP. Microsoft has put together extremely good resources on OpenMP. These are slightly long URLs, but you can Google it or look at the slides later. Ruud van der Pas has several good videos. He talks about more advanced, detailed ideas like the first touch. First touch is when you have sorry about the voice. When a core accesses a location, it gets to own that cache line. That has its benefits, things like that. Okay. I'm going to begin with one of the lectures I found from Texas A&M University. Sorry about the sound. I think the fan noise is causing it, maybe. Or that's okay. You can keep the fan. It's kind of comfortable, but I can hide the mic somehow. Yeah, it's okay. OpenMP by example is a good example. Please interrupt me anytime you want to ask questions, but I will now charge ahead. Okay. The basic architecture of olden day processors is shown here. We all know they were uniprocessors. It has changed and become multi-core, meaning multiple cores can address a shared memory space. Given that you can have a node with multiple cores, multiple sockets which contain cores. Even across cores, you can have a shared memory region that's arranged through cache coherency mechanisms. So when you buy a cluster, you'll find typically one of these big boards in it that has several multi-core chips, and the interconnect is quick path interconnect, or AMD's hypertransport. Those again give you a coherent domain, so that makes the shared memory available. There is also distributed shared memory, which we don't get into, but even across nodes in an in a distributed cluster, you can give the appearance of shared memory, but we don't discuss that here. So one instruction stream executes in a core. That's called a thread. Threads are allocated by operating systems. Operating systems these days have the ability to allocate thousands and thousands of threads. They all have a stack. The operating system maintains the context of each thread. Even the hardware knows about threads, so hyperthreading knows how to execute threads. Processors have memory isolation. Processors live in different memory spaces. They don't share memory. They have to message. So in today's climate, if you have a pre-existing sequential program and you don't parallelize it, you get this effect of running on one of the cores. It's almost like removing 3 of the 4 spark plugs of a car and trying to drive on one cylinder. That's the effect you get. You get that much horsepower. So we have to parallelize. So almost all existing codes that were sequential had to be quickly parallelized. Some of you already know OpenACC. Who is that? Yesterday I spoke to the gentleman here. Okay, OpenAC. So that's another one way. OpenMP is the standard way of doing it. It's widely available. Yeah? Left side is better. Thank you. This is working better? Okay, thank you. That way the air pickup will be low. Yeah. Thank you. It can be inside. So OpenMP is the way to parallelize. It's available for many languages and dialects. How an OpenMP compiler works itself is important to know, but I'm not covering it. But the basic idea is that OpenMP's main job is to attack loops and make the loop iterations go parallel. So when the OpenMP compiler encounters a OpenMP loop, it really outlines the loop body as a function. It creates a copy of the loop body as a function. And then that function becomes the work item that the threads then engage in. So there are P threads underneath. P threads are the ones, or other threads, they run the loop bodies. And you can actually see this even when you write OpenMP programs. I'll tell you quickly, we'll revisit it later. If you write a double nested loop and parallelize the outer iteration for I equal to 1 to something, for j equal to 1 to something, the I becomes the shared variable because that's shared across the iterations. The j becomes the private variable because the loop body after the I is outlined as a function. I becomes a local. Scoping in OpenMP is very important. To know which scope in which variables live is very important to know. If you do not refer to the variable in the private space, in the correct scope, you won't get the right results. We'll have to look at that. And again, I'll tell you a quick fact. It may show up later. If you write a for loop with for I equal to 0 something, that's one way to do it, where the I is then referring to an I in the outer scope. If you write for int I equal to 0, something like that, in modern C11 or C99, that is a locally scoped I, because for int I, it's declaring the I there. So that itself changes the scoping of the I reference later. And it's a good way to cultivate that habit. Always locally scope iteration variables, because the worst thing that can happen is some variables become too private, and then you don't get the sharing. Then you will notice that and fix it. Too much sharing to begin with is often bad. You can introduce sharing when needed. Yeah. Anyway, so these are all, there is an interplay between the language given scoping rules and OpenMP. This is what I'm referring to. I will have hello world like examples in my slides. I won't talk about these slides. I'm not going through this entire slide suite, but it's available online and you can look at it. Maybe we'll look at it selectively because I don't have all these good pictures. So the basic idea is that there is always an initiator thread that starts the program, which is the normal thread that executes the main. Then additional threads are created as a thread team. It uses the fork join model. I'll have good slides on these. Okay, I'm not going to go into this presentation too much. I just wanted to use some of the copies of good examples here. So let us now switch to one line of presentation that I have in these notes, which I created for my class earlier this year. So let's go through all these examples very carefully, make sure we all understand each and every example. So the objective is that if we understand all these examples today, you should be able to go to the lab and write a matrix vector multiply yourself. That's the kind of exercise that I have in mind. Okay, so this is a C-style OpenMP program. Generally, C++ style doesn't have these includes. It does different, but it doesn't matter now. Main program. So you can get the thread count from the argument V list. This is an OpenMP program. Sorry, yeah. It starts looking like pthread sometimes, but I look for a pragma. So as soon as I see a pragma, I think it's open. Yeah. So you can get set the number of threads from an environment variable, or you can actually pass it through the command line, etc. However you get the thread count. The main signature of an OpenMP program is that you have pragma OMP parallel and then num threads, thread count. So this is a typical parallel section in OpenMP. One of the parallel sections we'll focus on a lot. What it does is it starts a parallel region. So a single thread was entering this parallel region till now, main, and now that splits into, let us say, thread count equal to 4, let us say. So I'll use blue maybe. So 4 threads are started. They all run this hello code, and then after that section ends, they all rejoin to become one thread and then return. So the scope of where the pragma applies is the immediate statement. So pragma OMP includes the hello. It's one compound statement, one statement that it includes. So a good practice to write OpenMP programs is also to write a pragma OMP, all that, and then write a block. That way you are not making any mistakes. You can always write statement A, statement B, in which case both are included in the parallel scope. That's just to avoid mistakes. Even for a single hello, it's not a bad idea to write a curly brace around it. Yeah. So let us look at a program that fills a table of sine values, sinusoidal functions. Whenever possible, I cite it as to where it came from. Okay, so there is already one difference we can notice, and let us see what this program should have done. I forgot to tell you that. So what's the effect of this program going to be? Let us think about it. So 4 threads are going to run the hello work item, which happens to be a function. So each of the 4 threads executes this. So they all get my rank, their thread rank. OMP get thread num. So it'll know I'm thread 0 of 4, I'm thread 1 of 4, etc. So thread count is going to be 4 in our example. This my rank will be 0, 1, 2, or 3. So the printout will say hello from thread 0 of 4, 1 of 4, 2 of 4, 3 of 4. That will be the printout that you will get if you run this. We will run it and see. This is one of the simplest programs where there is absolutely no coordination between the work items. Each hello invocation runs in parallel using its own operating system provided thread, and they all join into the main thread and come out. Okay? Questions? Anytime you can ask. Let us now come to the sine table. So let us dissect the program. Main starts here. Okay, so we have a constant declared, a sine table of a certain size declared. Again, now look for the main parallel sections in the program. Pragma OMP parallel 4. This is a compound construct. Pragma parallel OMP 4, and then this need not be a for loop. This could be any other section also. But what I'm going to say is the following. Whenever you see a Pragma parallel OMP 4, it is as if you wrote Pragma OMP parallel and then So it's a combination of these two that is expressed as a single construct. So pragma OMP parallel followed by pragma OMP for, and then the iteration, the for loop here. This is a frequently occurring situation. So the main general construct that you have in OpenMP is pragma OMP parallel, pragma OMP parallel. That's what we used here. See, pragma OMP parallel. That's the main creator of parallel work. How it can create parallel, who will execute the parallel work is the next question. So when you start pragma OMP parallel, and then you can have OMP sections, section, OMP section. I'll give you the syntax later. This is another possible thing that can hide under pragma OMP parallel. It can be pragma OMP section 1, pragma OMP section 2, pragma OMP section 3. This is another alternative where each section will be picked up by one of the threads. So if one thread executes this and you have created, let us say, 4 threads here, then another thread can pick up another section, etc. So once you start to work items using pragma OMP parallel, you have launched a collection of collection of threads. That's called a thread team, and then the thread team's job is to attack everything that lies underneath. So if it sees sections, it can attack each of the sections, each thread. But if it sees a pragma OMP parallel for, then each of the threads that you join and spawn attacks one of the iterations of the for. So each for is opened up as if into multiple iterations, and each thread goes to work on one of the iterations. Since this combination occurs so frequently, pragma OMP parallel and pragma OMP for always occurs together in many applications, OpenMP provided a single construct for the convenience of the programmer, which is pragma OMP parallel plus you add this for here. So that immediately tells you that the work items that are the thread team that is created by the pragma OMP parallel has to attack the immediately following for loop that is found here. That's where the work items go to attack. Now you have to make sure that it is possible to parallelize this loop body, which means how can I tell you? Okay, here's how you have to think. Let us say that you are a programmer who had a serial for loop before and you want to parallelize it. The only loops that can be parallelized are those loops which can be run in any order. So suppose you take a for loop, you go from for I equal to 1 to 100. Now the same for loop makes sense to run for I equal to 100 to 1 or anything like that, for I equal to 50 to 25 to 78 to 1 to 25. The loop order doesn't matter. Each iteration is independent. So that's the mental test you can subject to. Can I run this loop in the reverse? If it passes that test, then it's a parallel loop, kind of. But if there is a loop that does for I equal to 1 to 100, A of I plus 1 equal to A of I, I'll write it in the syntax. If you have A of I equal to A of I plus 1, in this sequential program, is it safe to run the loop backwards? No, because the intended effects don't happen. So these are loops where there is a loop carry dependence, which means one loop iteration feeds into the other loop iteration or the other way. So the dependence analysis is a long series of discussions in OpenMP, which we have to discuss separately. But the idea is that each loop iteration has to be thought of as an independent parallel activity. And now you can see whether the ordering of these parallel activities is order independent. You can order them in any which way. It is like shuffling a deck of cards, you see. So if one thread is T1, another thread is T2, a third thread is T3, so So you have to think of threads as looking like a deck of cards. Now you all know how to riffle shuffle decks of cards, right? Like that, 2 card decks. Imagine 3 decks of cards, riffle shuffle. That's the number of interleavings you get. And it's possible to calculate that. It takes a second, so let us calculate it. Just because you will be, if you haven't done that, you should do it once at least in your life. So if I have a deck of 3 cards here, deck of 4 cards here, uh, 5 cards here. How many riffle shuffles are there is the question. So you can place this one, then this. Of course, you can't take that one. You have to go in order. So the next eligible card may be that, then this one may be, then this one may be, like that. You see? Yeah. So you're riffle shuffling it into linear order. I'll give you a quick calculation. If you don't understand the math, you can ask me later or think about it. So the first thing you have to think of is throwing all these cards into a hat and shake it and put it on the ground in some linear order. So there are 3 plus 4 plus 5, 12 cards. So you can get 12 factorial arrangements of those. But many of those arrangements are not intended, because there is only one arrangement. You don't want this card to be before this card. So you have to divide out by 3 factorial, divide out by 4 factorial, divide by 5 factorial, things like that. So you can calculate the number of interleavings very easily like this. This is a huge number. That's the point. If you have 5 decks of 5 cards, 5 decks of 5 cards, the number of interleavings is 16 trillion. That's the combinatorics. So we don't see all these interleavings. Any of one of these can happen, but if there is any dependency between the loop orders, one of these interleavings may be the one that shows the bug. And now the job of bug hunting is job of hunting this bad interleaving out of 16 trillion, which is almost never shows up in testing. Testing is not a good answer at all. So you really had to sort of use a compiler and check whether the loops are loop order independent, things like that. And debugging, the problem with concurrent debugging is because concurrency gives you so many shuffles of the thread's activities, and one of these shuffles could hide a bad interaction because you read a variable before you wrote when you intended to do the other way. And if that hides in the 16 trillion space, and 16 trillion is a small number, we don't have 5 threads, we don't have 5 actions per thread. We may have 1,000 threads, we may have 1,000 actions. So these things multiply very fast. And this is why conceptually parallel programming is clean if you have completely independent local activities, but as soon as one read-write coupling happens, it becomes a worry land. Okay, I just have to give you this math. So back to here. So we are now looking at the sine function, and we sort of know that the loop iteration orders are should be independent. And let us look at the loop body. The loop body of sine is, each thread is picking up the nth entry and wants to fill that sine function table. So are the loop iterations independent? Are they? Yes or no? They are. Because each n is a different entity, there is no n-1 reference to it. So in a statement like if this had, suppose this had, for some reason I wanted times sine table of n-1, then there is a problem, because one loop body is making a reference to another thread's work item, variable that is manipulating, and the order then matters. Okay, so this loop is a parallel loop, or this loop order doesn't matter. Okay, now look at this comment. It says this for loop is done serially by one thread. Why? Sorry? It's an output function, that's true, but let us look at the rules of OpenMP that tell us. So pragma MP4, and then it is going to look for one statement coming after that. The author didn't use a curly brace, so this statement is the compound statement that it parallelizes. So the obligation to parallelize ends here. At that point, all the threads that were spawned converges to one thread. Okay, so the other thing to understand is that pragma OMP parallel is going to create a parallel region, but it ends in a barrier. So this barrier is automatically inserted by the OpenMP compiler. I'll tell you what a barrier is, but conceptually the barrier is a point at which all the threads have to wait for each other. No thread can cross unless every thread has caught up. So that barrier is implied there. So what I'm going to now say is, if you have a situation of pragma OMP parallel, I'll write it as I'll write it in a new page, sorry. Well, I can do this trick. Sorry, I should keep tapping this. To connecting the power supply. So it's okay. So I have 3 copies of this. So if you have this kind of a code where you have many pragma OMP parallel fors, there is a problem. This code has too many barriers because each of them ends in an implicit barrier. Barriers are a net performance killer. First of all, barrier execution itself is bad. The second is that maybe this thread could have gone ahead and started doing the next for. Why make it wait for the other threads? So when you have this kind of code that you are about to write, you should immediately change your code to parallel. You get the idea. I'm just showing off my ability with this tool. Cut and paste. Okay, so this should be the code that you write finally. Pragma MP parallel, pragma MP4 for 1, pragma MP4 for 2, pragma MP4 for 3. If you write it that way, you get the effect of the same thing, but with only a barrier here. So one barrier is going to be ending this parallel section. So these are all things that one keeps in mind when using OpenMP. First, keep in mind which loop you are parallelizing. Is the loop order iterations, are they independent? What construct are you using to parallelize the for loop? Does that construct have an implicit barrier at the end? And then you write the proper code. Okay, that's how you get to this. Yeah.
What about the two loops, like the 3 loops you have?
Yeah.
And the first loop that says, let's say I equal to A of I. E of the like copy
Yeah.
A of I is equal to B of I.
Yeah.
The second loop from like when we access in the other I is equal to 2 I.
Yeah.
How can we ensure that that
That is true. That is true. This cannot be always done. You have to make sure that it is okay to allow these threads to continue before another thread has finished its work totally. It can only be used when the loop or iterations here are together independent with the loop iterations here in a sense. You should not have to wait for all the activities to finish. If you wanted that, then you should go back to this one. Yeah. Yeah.
So what you run the pragma for loop open?
Yeah.
How many threads it will like allocate?
How many threads it will allocate? It basically depends on the number of threads you have requested from the system.
Okay, when you are like.
I'm going to show some details.
Okay.
But the system may not be kind enough to grant you all the threads also. You can say there's a set number of threads and you can say 200, but the system may give you only 20.
Okay.
Yeah, so you have to, there is a query that you can see, invoke to see how many threads that got allocated.
Okay.
It all, because even your operating system needs to play safe. It has allocated 200 threads maybe for your display, 500 threads for your network port. Finally, it has run out of threads. So it cannot take your wishes. And it's safely handled by the
Other question like if you have a pragma and the second bucket A and B, let's say A is another section and B is another section.
Yeah.
So how to do the first A will complete, then the B will complete, or?
Yeah. The completion of the sections is in the program order itself. Absolutely.
Okay.
But then it depends on which threads are engaged in which section and which threads are allowed to wait for the other threads in that section before you go to the next. Those are all details coming soon.
Okay,
These are excellent questions.
Thank
Thanks.
you.
Keep questions like this coming. These are all excellent questions. Yeah. So this is still the first example. So we'll go slow and easy and make sure everybody understands. So far we have made sure that this program is more or less well understood. You can type it and run it. Or these codes I can make available, or you can type some of them. Anyway, so this sign table function gets parallelized. All the threads are carrying 2 times pi times n. MPi has been deprecated, so you had to define it these days, but this is old code. I just ran into it recently. MPi has been discontinued in some of the C libraries now. Okay, but otherwise. So now this is it's printing the sign table. So when you print it and you can send it to GNU plot, you can plot the sign function. That's easy. You can just fill it into a text file and ask the GNU plot command. Have you used GNU plot before? GNU plot? It's a very nice program, free program, easy to learn and use. Recently, my daughter in 11th grade wanted a quick multinomial, binomials, etc. So I taught her GNU plot, and it was finally the fun thing. It gives you nice 3D plots. So for scientific computing, GNU plot is a very easy to learn, easy to use, versatile, free tool. It does nice 3D plots. Okay, so now we are going to go advice. So a lot of advice and a lot of indicators are coming. So advice, use curly braces to demarcate section. Anyway, it is natural to do that. In expert code, I don't find it, but I like to put it. Okay, the next slide. Noteworthy points coming in the next slide. Maybe all of them don't come. We'll see. Okay, so how about nested parallelism? That's the question that many people had. I had it. So suppose OpenMP's execution model is like this always. So start a fork join, start a fork activity, they join. Then fork again, join. And like I said, if you don't want to join, you can make it into a continuous flow by removing the barrier, etc. But that's right. But suppose here, this thread wants to create a nested parallel region. Is it allowed? And the answer is, it's being allowed these days. Old OpenMPs didn't allow that. But now nested parallelism is allowed in modern OpenMPs. Why would you want to do that? So suppose you use a math kernel library, Intel's math kernel library or those libraries. Those libraries are threaded. So if you let those libraries get executed by multiple threads, it will be faster. So that may be one reason why you want nested parallelism. So see how thread teams are started and converging by parallel. Requested number of threads may not be yielded. That was the question here. And I don't know whether this is needed, but a set environment OpenMP nested true is the way you turn on the nested parallelism feature like this in OpenMP. I don't know whether that is needed. It's good to know that there is a set option like that. You can always consult anything I say on the web to see what's the latest. These are all moving standards. But if it's allowed, when we get nested parallelism, this is how you write it. Pragma OMP parallel num threads 2. So you can say, I want to run only 2 threads in this parallel region. You can say that also. And then you can nest a Pragma OMP parallel num threads 2 as a nested. So that will take one of the threads that are entering here and then split that into 2. So maybe one of the threads is running here, and the blue thread is doing that, and the purple threads opens into 2. So these are the 2 threads here, these are the 2 threads here at this level. Okay, so now let us do some drawings and read this code. I pre-annotated it so that you have a good visual of what the code looks like. And again, these are available in the annotated form online. I found these colored annotations quite helpful when I taught it. A question? Was there a question? You just asked. Okay. Yeah. But yeah, so let us try to read this code. This is print laden's code, where the print statements will tell you what's going on. So OMP set num threads equal to 4. Hopefully the OS is kind enough to give you that. You will find out that later. So printf %d and then OMP get thread num, OMP get num threads. Okay, they look same, but one is get thread num, and num threads is the number of threads that the OS actually gave you. And let us see where that printout is. That printout is here. You see that? So I have all the printouts saved as comments at the end. So get thread num, it prints 0. Get num threads printed 1, and that's fine. Why? I have requested 4 threads, but are we in a parallel section yet? No. So there is a potential to start 4 threads, but till you hit a parallel section, it doesn't start those 4 threads. So it's only 1 thread that is still running. That's the main thread. Okay? So that's the detail. Okay. Questions I can discuss, or you can talk to yourselves, no problem. Okay. So then you have Pragma OMP parallel. So now you see 4 threads wanting to start. So notice that this is not a parallel OMP4. So you have decoupled the Pragma OMP parallel 4, like I said before, into Pragma OMP parallel. And then if you want for loop parallel 4 underneath, you can write it separately. But here we chose to offer other sections for it to run. So we gave it Pragma OMP master. So that means one of the threads which calls itself the master thread must run through this section. And you can trace its printout here. Master 0 of 4. You see that? So it actually tells you 4 threads have started, and master is announcing its thread ID, which is 0. I'm sorry? No other parallel work. So the other green ones are bypassing it now. Yeah, so they have not been given any work. If you had put a print statement here, those guys would have executed that. Yeah, so no other parallel work is done. I don't want to remove too many. Some of these annotations are interesting. I let that remain. All right. So now that's the printout, and then after reconvergence, so the reconvergence happens. Then you get a printout again, which tells get thread numbers. So back to 1. See that? So reconvergence. So learning OpenMP through prints is a useful way. You can write different OpenMP sections, put these print get thread num get num threads at every point. You sort of know how the control flows. Now I'm requesting pragma MP parallel num threads 3, and then pragma MP master, etc. Same thing. And no other parallel work like you mentioned. But the next example, I think, has parallel work. You will see the interleaving now. So this is clear how this program works. It's basically trying to show what the OpenMP sections try to do. Master is usually used to take some global actions of interest. So you usually start a master section when you want to print out. That way, not every thread needs to print out an array or things like that. You can just print out selectively. The other construct, such as master, is called single. So if you write pragma OMP single, then it means that any single thread can do that activity. Pragma OMP single doesn't have a barrier. Pragma OMP master has a barrier. You have to know that. I happen to know it, but this is a bug that comes into many systems. Single, any arbitrary thread, no barrier. That's how they designed it. For master, there is a certain more important status. They automatically provide a barrier. So yep. That's a very good question. I asked myself that. I didn't have internet to check it, but in all the experiments, I find it is 0. So the way to answer that question is to consult the OP standard. Okay? Yeah.
Thanks.
Yeah, thanks. Yeah. I will not safely say yes, but I think it is. Yeah. But again, it's not a good idea to, most likely I don't depend on the number of threads or the thread ID. That's also always robust programming, but if it is guaranteed by the standard, you should use it. Yeah. So OpenMP standard is available on the web, and it's actually, there's an OpenMP forum that tells you, at the end of these slides I have the OpenMP standards reference. But good question. I think the answer is yes, but I'll double check. Yeah. Noteworthy point, next slide. Node prints from parallel region, node schedule dependent print order. So that's what we are going to observe in the next slide. Okay, so slight variation of the example. The flows are shown. Okay, so the point of interest is here. So in master, I'm printing this one. The other threads are called slave threads. So in the slave thread, am I printing something? Okay, here it happens. So here in pragma MP parallel, all of them are printing, and then master alone is printing. Here then after reconvergence, something is printing. Then in 3 threads, master is printing this one. Then the master converges here. Then the parallel section ends here. So I didn't still provide useful work for the other threads, but there is a print outside. The thing is, some of these prints can interleave differently. That is the main point. So let us see. So these are 2 executions. I ran the same program twice here, and then I got 2 different looking printouts. That tells us that the threads have different speeds of execution. The prints can happen in slightly different order. So here, what did I get? I got 012404 master 04. Here, what did I get? I got 012434 14. Okay, here there is one more. I think this is one activity. So who put 0:1, 2:4, 0:4, and master 0:4? Let me see, how many prints do I expect? There are 4 threads, so I do expect 4 printouts. And let us see how the printing happens. Master followed by the number. Okay, yeah. So I totally expect 5 prints. Okay, I'm slowly looking at this program after a little while. Why 5 prints? There are 4 threads started here. So 4 items should get printed by this guy. And then in addition, the master prints 1 more. So there are 5 items that I need to see getting printed. And so if I parse this printout, 1, 2, 3, 4, 5. Here 1, 2, 3, 4. Right? Which one? Oh, there is a one print above the pragma also. Okay, that is true. So that can be discounted. Thank you. Yeah, that's not there. Yeah. So the counting is right. So 1, 2, 3, 4. Yeah, that's good. 5, I think. And then these matches 1, 2, 3, 4, 5, I think. Yeah. So even the so 0:1 is not to be looked at. 2, 0. I think I'm reading it correct, but that's the idea. So master is 0. So, and there is no prints other than that. But there are 4 prints here. So I get 0, 1, 2, and 3. So 0, 2, 1, and 3, and then master further reports 0. Okay. So those are the things. So here 2, 3, 1, 0, and then the master further reports 0. That suddenly wants me to log in. Okay. Thanks. Yeah. So oops, I'll turn off the. I think I'll turn off wireless if it happens again. Okay, so there are 4 prints and the master prints once more. So there is some interleaving of actions. Nothing, no other big point other than this one generates 4 printouts, the master produces 1 more, but the schedule of the threads shows up here. And then comes this convergence point, and then you have 3 prints by 1 print by the master, and then how did the reconvergence has happened? Then master prints once. Then there is a print here. Okay. I'm looking at the parallel sections. I'm kind of, I'm not going to spend too much time on this. This could be a point where we can dissect every print and make sure, but generally that's the idea. I will leave it at that. Okay. So now we had to look at other interesting constructs. We are going to first look at reduction. So when you do for loops, the general use of the for loops to create a new array of values, but sometimes you want to create a single value coming out of the for loop. So you may want to do a dot product, for instance. So AI times BI. You may want to achieve the effect of CI plus equal to AI times VI in a loop. And that's when you want to use a reduction. Reductions are needed to reduce all the values to a single value. So this may not be the right example. This is the answer. So this is the dot product here, dot product. We'll look at the example. So yeah, so it's good to always request the number of threads provided by the hyperthreading limit, not to exceed that, etc. So we'll come to that, but don't oversubscribe. This is called oversubscribing. If you ask for too many threads, more than the number of hardware threads, and the system allocates that many threads, then there is no net benefit. It slows you down. So oversubscription is generally not recommended. But the other thing to keep in mind is the data distribution. How do you distribute data across threads? This is a topic that requires some thought. The pros and cons of bad data distribution are you may run into fault sharing, and that's mainly it. So cyclic is the simplest is the simplest type of distribution, but the alternatives are block and block cyclic. So there are three kinds of distributions. Let us look at the colors and understand what they are. So cyclic data distribution is one where you allocate adjacent data items to two different threads. So cyclically allocate. That looks more natural because you can sort of say the index that you want to access is some base index plus the thread ID. So that way for each thread, the thread ID is higher and it allocates the successive items. So that's a cyclic. But usually this causes fault sharing. We'll look at an example, but the basic idea is that maybe this thread is accessing one location and this thread is accessing the next location. And then you get the fault sharing effect, which is that the data accesses are falling within the same cache line, remember the bone. So you don't want the bone to be sent back and forth. So the fault sharing effects will happen. So to avoid fault sharing, you may want a block distribution, where in a block distribution you make sure that one thread gets to access enough locations to completely fill a cache line, and then the next thread is accessing locations in the next cache line. So if you play with the indices correctly, how you index calculate the index determines how the accesses go. So you have to always keep this in mind to seek the more productive alternative. Block cyclic is a compromise where you sort of block it to a small degree, then you cycle through the threads like that. So these are conceptually defined, but now when you look at a piece of code, we should understand what distribution is being used in that code. That's the purpose. So look at a piece of code and name, oh, this code is using block distribution, or this is using cyclic distribution. Then start thinking of how the data accesses will go, pros and cons. So that's how the thinking goes. Now this is a heavily annotated code, a lot of drawings, so it'll help understand. This is written by Tim Madsen. So you begin an OpenMP program by stdioh, omph. You can define max thread 16, some long number of steps we want to do. What we're going to do is calculate pi using a simple series addition. There is a series addition that converges to pi. We don't need to worry about what it is. It's used in many examples. Double step and all that. And then you have started the main program. Now all these are shared among the threads. So these are all in the main scope. And when I'm going to start the threads, unless I tell otherwise, these variables are shared. You can always privatize these variables. That's an option given to you. But if I don't tell it, the OpenMP system happily shares those. Okay, so the first thing I do is to for. So that's there is no pragma here. So it's an ordinary for loop executed by the main program. For j equal to 1, j equal to max threads, j plus plus. OMP set thread. So what I'm doing is a speed experiment. Okay, so I'm playing with this program run under 1 thread, 2 threads, 3 threads, up to 16 threads. This can be useful for a speed test to see how scaling goes. That's why there is a for over number of threads where OMP set number of threads is the first thing I do for that. Okay. Then I do full sum equal to 0. Then I get the start time, get the time from the system. Now I begin my parallel activity with the number of threads that is allocated. So the number of threads that is allocated is j. J can be any number here. So with that I start my parallel activity. So then what do I do? Then I have parallel team which basically uses where's the scope of the parallel? Let us parse this parallel correctly. So what is it doing? So id equal to 0, it's all the threads are being launched. Yeah. Initially it will be 1, then it will be 2, then it will be up to 16. So at some point there are 4 threads. That's the picture we are looking at. So when the 4 threads are being launched, these variables get initialized. They are all private to the threads. So every thread knows its I and id equal to OMP get thread num. It knows its rank, and it knows what's the team size, etc. And they are all going to do sum of id equal to 0. Sum is what? Sum is where is sum? Full sum, yeah. That's going to be shared by the thread team. So sum is shared because it's outside the thread team creation. So the sum array is going to be shared by all the threads coming in. Fortunately, each thread is only going to write into its place. The sum of id is its own location. So they are not contending on one common location. That's good. We don't want to clash on one location. Otherwise, depending on their speed, they'll clobber each other's value. So sum of id equal to 0. So they're all initializing their sum variable. Thread 0 sum variable sum 0. That's set to 0. Sum 1's variable is sum of 1. That is set to 0 by thread 1, etc. That's what is going on here. Now what happens? If id equal to 0, this is one way to explicitly say I'm kind of master, but it could not be master. But whatever thread id is 0, it says num threads equal to, it will give you a printout. And then for id equal to, okay, so now we have to see, is this for loop iteration, are these for loop iterations being shared are the iterations of this for loop being split apart and worked on separately by the threads, or is this for loop entirely executed by each thread? That is the thing that we have to understand. So to understand that, you see whether this for loop is under a pragma OMP for. Is it? It's not. It's not a pragma OMP for. So it's an ordinary for loop. So you started a thread team here, but they're all carrying out this entire space of for loop. Okay. So these are all combinations allowed. But now you can see what this for loop is doing. For I equal to id, I less than num steps, I plus equal to num threads. So thread 0 is starting at I equal to 0. The next point for thread 0 is 0 plus num threads. So if the num threads is 4, the num thread, so this thread 0 is going to now look at 4, 8, etc. So thread 0's access is sum of 0, sum of 4, sum of 8, sum of 6, 12, etc. Thread 1's access is sum of 1, sum of 5, etc. Now if you draw a picture, you know it's cyclic. That's what cyclic distribution means, because each thread is asked to access its location and then num steps later, num threads later. Sorry, what?
To make cyclic distribution, we need parallel for.
cyclic distribution, you don't need parallel for the indexing that is being provided here by the different threads. Am I not right? So here each thread is doing this for loop, but this for loop is now further governing how sum of ID gets accessed.
Yes.
But I'm now looking at accesses of this sum of ID with respect to thread ID 0. And thread ID 0 itself is starting at I equal to ID. Okay, yeah. So, okay, I equal to. So, I think I made a little mistake with the ID. I should take it back. I was mixing ID and I in my mind. But I think the gist of what I said is true, but let us check everything again, okay? Okay, so what is happening here? So who is indexing sum? So sum is getting indexed by the ID. That's clear. And ID is flowing here, so ID could be 0, 1, 2, 3, etc. That is clear. In this case, 0, 1, 2, 3. So sum of ID, so sum is getting accessed in a cyclic manner directly. Yeah. So sum is like 0, 1, 2, 3, like that, this way. And then ID is increased only for the next team size experiment. The thing that I confused momentarily in my head, thanks for the question, is for I equal to ID. That's what is doing that. Okay. That's an interesting step. What it is now doing is it is asking thread I to do this calculation, x times step, x equal to I plus 0.5 step, and then there is a little series that we are adding. So this final series that we are computing is, I should have written it before, 4 divided by 1 plus x square series has to be done for the entire range. So that's the series that we want to evaluate. 4 divided by 1 plus x square, where x is defined to be I plus 0.5 times step. So this is so thread 0. What is thread 0 going to do? Thread 0 is doing this for loop. How many times? Num step times. In num step iterations of thread 0, it is okay, so yeah, that's right, yeah,
So that will be different.
that will be different.
So it is that I think as
Yeah.
you said before, it's right. I think.
Yeah, so the basic task that each thread is allowed to do is to add up a series of values hopping over gigantic steps like that.
Yeah.
That's right.
With the indexing, it is making like that.
With the indexing, it is
Indexing.
making like that. With this first thread, it is jumping like that. Yeah. So it is doing a series addition, but in a block of values which are non-interfering. So thread 0's charge is to add up this chain of values. Thread 1's charge is to add up that chain of values. And it is depositing the answer finally back into sum of ID. Yeah. So the finally sum, if you had 4 threads, sum 0, sum 1, sum 2, sum 3, would be the final answer, where the final answer is there momentarily. But sum 0's answer is a sum of this calculation done over 0, 0 plus however many threads, 0 plus however many threads. I had to see the full numericals. There's a big sigma that I have forgotten to write, sigma equal to 0 to max of the series. But that sigma chain is being split up by the thread saying, I'm doing this sigma, I'm doing that sigma. And then they're all bringing those sigmas and adding it together. That's the algorithm. Sorry about that. Yeah, these are good discussions. So, where's J? Okay. So the j is being set to num thread, max threads. So j is the variable that I'm just playing to set the num threads. So this is different experiments. Let us run it for 1, 2, up to 16 threads. Yeah. So this experiment is now saying, so full sum is being added to the band. So finally, like we discussed, the answer. So the answer is found where? This is a good question. So if I have 4 threads, the relevant answer is a partial sum is found in location 0, 1, 2, and 3. Yeah. So the relevant partial answer is found in here. So j is allowed there. Then when I have 5 threads launched, the relevant partial answer is 0, 1, 2, 3, 4. Then it is going to accumulate all of that. So this is partial sum, and then the total sum is being done. So this is the full addition, which is now going as a serial sum. So finally we say we have reduced a humongous series of values to at least partial sums, one belonging to each thread. And now we have to somehow add them up. That's what is going on. So there we use a serial sum as a first example. It's not the best, we'll come to other alternatives. So that's the first solution. Okay, so good. We are reading this code minutely. And the nice thing is you can run this code, and I also printed the actual printout here. So when I ran this experiment for 1 to 16 threads on one of my machines, I got the timing like this. You see how it's going. So one thread executed the whole calculation in 0.92, then 1.16, that's just, 1.16, and then 0.9, 0.8, 0.8, 0.7, 0.6, 0.68, 0.77, 0.8. Okay, it's not very, is it scaling? It's scaling somewhat, but very, very poorly. More course is not giving me a net increase, and after I think the hyper-threading limit was 12, I think, in this machine. So at 12, I start seeing net increases from then on. So now we have to diagnose this problem, see what is going on. Why is it not scaling well? Once it compiles and all the core dumps later. So the first few experiences will be core dump, seg fault, then something runs, and then finally you get an answer. In C programs, that's a development cycle. Okay, so then we see what's going on. The first thing to know is, how do we know it? Somehow you have to know that something is hurting performance. First is intuition, saying what could be the reason that it is slowing down. You look at the accesses to see if there's fault sharing. Maybe there's fault sharing, then adding padding will help. Padding means you move the accesses some distance apart. How do we know it for sure? Well, you have to use a tool such as HPC toolkit, or use performance monitors and see if L1 misses are high. So there are very objective ways to look at cache misses, and if L1 cache misses are very high, it is told by many books. I haven't tried all these myself. I hope to one day. I did try HPC toolkit. It's a nice toolkit. You can actually get it from the web on GitHub. It gives you a very nice drill down into which function is taking how much time, line by line description. So use some good profiling tool and somehow understand there is some performance issue. This is a long and complex story on how you detect performance bottlenecks. But of the two tools I have tried, I tried Tau and I tried HPC toolkit. HPC toolkit installs very quickly, readily, and it's well supported. Tau is very widely used, but it needs more steps. Anyway, so here we think of the program hard and somehow understand there could be a problem there. And this is Tim Madsen's example. If you watched his video, he will pretty much tell you, yeah, this is why it is hurting. So he suggests a solution. That's a solution. what are we doing? Instead of some max threads, we now have some max threads with a padding pad. What is it doing? It's wasting space. It's basically adding a second dimension called pad, but you never access in that second dimension. So it's like a 2D array where you sort of, so the next location that you get to access is further down. So in pictures, this is what is happening. The pad is the blue region that we add. So if you have enough memory to waste, which is rare, but if you have, then thread 0's accumulation will be here, thread 1's accumulation will be here, and this could be the cache boundary. So you are pushing the partial sums being created by the threads to be padding distance apart by a certain factor. Sometimes these solutions are inevitable in the scheme of having allocated enough memory. Maybe this is available, but you have to always worry whether this is the right solution. But in this case, you don't need to use padding, you can use block distribution. So the best answer here is not to do padding, but to change the allocation from cyclic to block. So you can achieve that by specifying a blocking factor to the loops, and that's coming next. But at least to diagnose the problem, we can add padding to see whether the performance changed. So here are the performance numbers, and see, you already see a benefit by adding padding. So from 0.9 it became to 0.4, which is nice. So even here we got a half in speed, half of their time. Here, even adding here it was not that. Here actually it went up from 1 to 2, it went up. So there is a distinctly fault sharing going on. So again, when you do the locality experiments today, you will see even a simple sequential program that adding padding is dramatic, or fault sharing is a net killer of performance. Yeah, so this goes 0.9, 0.4, 0.3, 0.2, 0.18, 0.13, 0.105, 0.09, 0.8, and at 12, magically at 12 it starts increasing. And the hyperthreading degree of this machine is 12, we knew that. So it was a nice trend at least, so there is performance. Yeah. Okay, noteworthy next point. How did we do the addition? We did serial addition here. How about making that addition somewhat less costly, because any serial bottleneck this is like this is bad for Amdahl's law reasons. We have 5-10 more minutes, right? Yeah. So variable involved in the operation is declared atomic. So we are going to change the way in which we are going to add. How are we going to do it? So the program largely remains the same. The only change we did is this is still the same. We use a sum variable instead of a sum array. Where is the sum declared? Here. So each thread has its own sum variable. And then here it's still doing the cyclic distribution, getting the sum established. And then what it is doing is all the threads are running through this and adding into pi the value of sum at that point. Okay, about 10 minutes or so. Yeah. So at this point we are now going to accumulate the partial sums into one variable, and that's a contention point. We can't just willy-nilly add, so we had to make it into a safe addition by making one thread add at a time, pretty much. There are two ways to do that in OpenMP. One is to use Pragma OMP atomic. The other is to use Pragma OMP critical. And we'll look at both uses, pros and cons. So ProMP atomic means this variable is going to be made into a special variable. Special variables are important in parallel programming. I already told you one special variable yesterday, which is the Java's volatile variable. You can think of special variables as variables on which you have sprinkled some holy water. Okay, that's what special variables are. They become holy. And when a compiler sees a holy variable being, a special variable being allocated, it automatically inserts fences and makes the concurrency safe. It's a very efficient mechanism. Modern compilers use all the fences available in the microprocessor to just push out the right amount of cache buffer, purge the right amount of caches, things like that. So it is very lean and mean. You should love atomic variables. Their cost of accessing are much, much lower than mutexes. So Amdahl's law allows atomic variables, volatile variables. The variable name volatile is unfortunate. C volatile has nothing to do with Java volatile. The amount of confusion in this area is just so staggering that the books need to start mentioning these in bold red fonts. C volatile is such an old ancient notion when there were printers and IO ports where they didn't want certain variables to reside in registers. So they used to sort of force memory activity. But C volatile variables don't help you with concurrency errors. So and I'll tell you something, NVIDIA used to have its manuals recommending old C volatile variables up to a certain point, but then later editions they removed it. So companies are also catching up. I mean, nobody is more knowledgeable than anybody else in this parallelism game at this point. Many experts have emerged, but in the 2000 to 2012 era, all experts were struggling to really define these languages and compilers. So the upshot is you should understand these types of variables as being the modern rescuers of parallel activity. One is Java volatiles, if you're in Java. If you're in C++ 11 or later, you should like C++ 11 atomics. These are the holy variables that you can trust. In C#, I think it's called C# atomic, I think, or something like that. Each language has its own holy variables, but not the old C variable. Okay, so this means that there are enough fences that it is not as heavy as mutex, but it still gives you critical sections. Okay, so a few more slides later we can have tea. Okay, so now we are going to use critical section instead of atomic to perform the same activity. So the way you understand that is you compare this code with this code. Now the only change is we put in pragma OMP critical. This is another way to achieve the same effect of contention-free accumulation of the sum. The advantage of critical is it can span multiple statements. Atomic applies only to one statement. One variable is called atomic variable that gets atomically operated on. Critical section, you can put a curly brace and put lots of statements after that. In atomic, you cannot do that. Okay, that's the main difference. But critical sections are costly. And again, wherever you introduce serial bottleneck, performance scalability will go down. Okay, one more, I think there's a nice point. Finally, we can use a reduction. So there is a best alternative. Don't accumulate a partial sum using all these mechanisms, but rewrite this loop as a pragma OMP for reduction. So there was a step at which every thread was calculating its own partial sum, going through its own lane of values, and then we had a critical or atomic add. Instead of that, we can write that as a OMP for reduction with plus as the sum. So then OpenMP gives you parallelism for this for loop, and the variable is already mentioned saying this is my reduction variable, and the operator is mentioned, that is my reduction operator. So at that point, OpenMP gives you a reduction tree of some shape. Where there's some value from thread 1, some value from thread 2. This whole thing goes into the final sum. So that tree is built for you. I had to probably get let's pause for tea now. Yeah. Thanks. Let's get some hot water.